So welcome everyone to week 2 in cardiac. So hopefully you've had a chance to look through some of the online content for this week, because we've gone straight into 12-lead ECG interpretation. So the plan for today is to talk about the different elements that we've added beyond the 5-step method for the 12-lead ECG interpretation. So talking about things like axis deviation, ST segments, and T waves. We've got a workbook which is on your summary page on Milo, so your tutorial 2 summary page. So if you want to access that and download it, then that will help you to go through everything as we go. Aside from that, maybe just a little bit of housekeeping. So I know that some of you guys have been emailing me, and I'm really sorry about the slow response of my emails. I'm slowly catching up, so I think I'm about 1 week behind my emails at the moment. So if it's anything urgent, please give me a call. Otherwise, I am trying to slowly get through the email chain, but we're just catching up after HSP1. So I'm sorry if you've been emailing me, and I'm sorry to get back. In saying that, on the summary tutorial 2 page, there were a couple of questions that I thought we could get straight into at the start, and sort of put it out to the room about what you guys think about some of these answers. So obviously you've covered some elements of 12-lead ECG placement throughout your degree, either on road formally or not formally. And I know that you've been doing a little bit with Clinton in your placement unit. But there was a question on the Padlet about limb lead placement and whether or not that is affected if we move our limb leads to our torso. Does that affect our ECG interpretation? And I just wanted to put that out to the class and see what everyone sort of thought about that or knew about that. Or some guesses.
I'd say that the limb leads, as long as they both either kind of on the wrists and ankles, and then or both on the shoulders and hips, I think that's okay.
All right. So we've got a vote from Tal that it's okay. It's same reading. Anyone else got any other thoughts? So Gareth is saying that the tutor last week said that the ZOL is actually calibrated for torso placement. Interesting, Gareth. Yes. So in that instance, do you think it would affect it the other way around if you put your limb leads onto the wrists and ankles? So from Emma, she says that it can't because it doesn't give an accurate view. From John?
Just with placing them on limbs comparative to torsos, I've noticed that you just get a lot more artifact when you're placing them on limbs. If people don't keep their arms and legs still and so forth, you just get that movement on the isoelectric line. So a little bit more harder to read. So I think I defer back to the torso just for more accuracy of that. But does that seem reasonable?
Yeah, it's a really good point, John, and it's a large part of why we have this torso placement, right? Or the limb lead placement, and why we're talking about it, because a large reason that especially paramedics do it is to reduce that artifact. I'm sure that you guys have all seen when you put it on the limbs and then someone's moving around and you've got that wandering baseline, or you've got that kind of artifact, I guess, this googliness along your ECG tracing. But the short answer is what some of everyone's sort of been alluding to is that it depends on your ECG machine, but really it's either calibrated to the torso placement or the wrist and ankle placement. If you were using an ECG for diagnostic purposes in hospital, you would have to do your wrist and ankle placement because that's how the machine was calibrated, because otherwise you get an inaccurate reading, and you can actually have false positives for like myocardial infarctions or bundle branch blocks. And there's a little bit of literature, which I'm going to link in the Padlet in response to that comment in the Padlet about some of the different examples of where there's inaccuracies kind of seen. But in summary, basically you have to know what your local ECG machine is calibrated to, and then whatever positioning you do, if you do an opposite positioning because of logistics pre-hospitally, then you need to write that on the ECG and say, this was a torso limb lead placement. It was used because we couldn't navigate the artifact from the limbs, but we had to do this placement because of the artifact. So then that becomes an ECG that they won't actually reference as a diagnostic sort of point. And that's especially important when we see something like an MI or something where we're trying to monitor that progression of that condition. So then they won't refer to that ECG so that it's more accurate. Yeah, go on, Tal.
2 questions. One, what is the core pulse set to? And that's the first question. And the next question is, how do we know what it's calibrated to?
I actually don't know what the core pulse is set to. So I'm going to have to get back to you on what the core pulse is. I don't know if anyone who works for New South Wales Ambulance is able to answer that question. Chloe has said that either the core pulse can do both. I'm not 100% certain about that. But the way that you do that is just by looking at the manufacturing instructions. So you just download the instruction manual and just see what it's calibrated to. In general, it's kind of weird that as paramedics, we're like, oh, we have to go and refer to the manufacturing instructions. But if you ever do like a quick care or HEMS sort of assessment, often they have, you have to know your manufacturing instructions to be able to kind of pass those assessments, because that's where things go wrong pre-hospitally, is that we don't account for the things that the manufacturer kind of designed in that. Obviously, we're talking very generally here because we're talking about ECG interpretation across different sorts of monitors. But I just wanted to signpost that question because it's going to be different depending on which monitor you use. But Tal, maybe you can come back to me with the answer of that next week. Anita, have you got anything else that you want to add to that? Or has anyone got any questions in relation to that?
No, I only just support what you said. Different machines will be calibrated differently, and they usually come with a manual, and they'll usually have that highlighted. So just to make sure it's diagnostic, this is one of the checks you do. Make sure limb placement, but also bandwidths of hertz, paper speed, all that sort of stuff, which I'm sure we're about to talk about. It's just another check to to ensure that the machine that is diagnostic, so therefore you can interpret the ECG.
All right. So are we happy to move on from that question, or has anyone got any more questions about limb lead placement? No? All right. So we're going to move on to our whiteboard. I thought I'd just highlight for everyone online, we've got access to this whiteboard for the rest of the semester. So you should be able to see it throughout the rest of the semester and access it in your own time. So just whenever you need to access it, just you can access it whenever you want. So I'm going to work on page 2 today. So I'll try and put them as different pages within each week as we go. So as I said, our learning objectives for today is about primarily looking at 12 lead ECGs. So we're going to start off with our safe elements for our ECG tracing. So hopefully on your ECG learning this week, you'll have covered sort of these safe elements, which is about the speed, amplitude, frequency, and ECG electrode placement. So to start off with, either in the chat or onto the whiteboard, do you guys want to pop in what our expected speed should be for our ECGs?
In the chat, all the 25s are coming in millimeter.
Amazing. So, yes, so we're looking at
Per second. I was waiting for that. Thank
yeah. Looking at per second. So our 25. What about our amplitude? And how would we check it? Trying not to refer to your notes through this so that we trying to recall and practice. But yep, Alison and Chloe, you are correct with your 10 mils or 1 millivolt. What do we look at to try and confirm that for both of them? There's a little thing on our ECGs to help us give a hint about how we look for this.
It's written at the bottom of or at the top of the ECG paper.
Yeah, 100% tau. So your speed should be written at the bottom or the top of the ECG paper. And then Chloe said it should be a deflection mark on the trace. What does the deflection mark look like? Yeah, the core is talking about the calibration thing. What will it look like and how big will it be?
Is that the rectangle thing at the start?
Absolutely, yeah. It is
Yeah.
the rectangle thing.
Like a centimeter tall then? Maybe, at a guess?
I guess it will be a centimeter tall, but I guess it depends on the size of your ECG
Ooh,
paper.
okay.
But it is 10, yeah, it is a centimeter tall. So if it's calibrated sort of accurately, then it will be a centimeter tall. But it will be 2 of the large squares. Is that right, Anita? So will it always be a centimeter? Is it always calibrated to 10 mils on the ECG?
I think so. As
Yeah.
long as it corresponds, like you can break it down. So as long as you've got you can look at it as well and look at the small box and the big boxes. And knowing how much each of those are worth, you can look at it manually as well and then correspond across.
But yes, so it should be 2 large boxes, and that is that weird sort of square thing that's next to your ECG. So why would we change the amplitude? Has anyone got any ideas about why we would need to change the amplitude? Or why would anyone in hospital do it if we can from Cora, just for fun? So it should be 2 boxes, but why would we potentially try and make it larger? So Gareth suggested maybe for different electrode placements. Kate suggested to identify more details. Zoe may be an obese patient. All right, so we're getting to some good answers here. Visualize something better. Yes, Chloe, if we can't read the different leads, there's not much electrical activity deflection. Fine VF, absolutely. So obviously sometimes when we look at our ECG, sometimes it looks all perfect and nice. And we can see all of the things that we need to look at from our waves and segments. But sometimes, for example, if someone has quite a large chest, or as I think Zoe's alluded to, if we have someone who has like a large amount of adipose tissue, sometimes our amplitude can't be seen as much. So we might have sort of that smaller spikes on the ECG waveform, and so we can't actually see those waves very well. So in those cases, certainly in hospital, they change the calibration of the ECG machine so that they can see those waveforms easier through sort of like those things like your adipose tissue or the larger barrel chest. So that's why we would change our calibration. But if we do that, it is important if you're like handing that over to hospital that you really highlight that, like make it obvious, you know, right all over the ECG machine, say calibration is not at 10 mils or millimeters. So they're the sorts of reasons that we would change amplitude. What about our frequency? What should it be? No one's got this.
Why is it important? So 1 to 1.5, 1, 1.5, I'm just
We've got 0.5 to 150, 0.5 to 105.
hertz is the unit of measurement. Yes, good, Chloe.
If someone else has got any other ideas, you can like someone else's comment. Got from Chloe, 0.5 to 150. Yes. All right. So in general, in most of pre-hospital settings, we either have 0.05 to 150 hertz or 0.05 to 40 hertz. But what is the sort of rationale behind that, as Anita has said? Any clues? No. Anita, do you know much about the reason that they changed the hertz?
I just think that we're in an unprotected environment, so we need to have it's a more narrow bandwidth hertz. It's what's usually in frequency than what's usually used in a hospital because they generally have protection from electromagnetic force or that can interfere with the reading. So that's why we have a narrow width generally in pre-hospital environment. And it's just important to make sure that it's set again when different machines will have different operating frequencies. So when you do your diagnostic check in the morning, it's just important to make sure that it sits within that bandwidth that you've got there. It depends on the machine, Gareth, yeah. And so usually it depends on the machine. It can be as high as 150. Some of them are like 40 to 60 or 0.5 or 0.05. It's usually 0.05 to 40 or 60 depending on, but it can go 150. It depends on the machine.
Sorry, so as long as it fits into that band of 0.05 to 150, anything within that range is acceptable.
And most hospital ones, as Anita says, goes for 40 or 60 because once you start to go into that 150, it becomes, I think it picks up too much interference and you have more of the artifact.
That's right. It's just protection for us because we're in an uncontrolled environment. We can't sort of, we can't predict where we're placing and using the equipment. So it's got to be protective for the uncontrolled environment. Similar in hospital where you're, doing scans, MRIs, X-rays, all that sort of thing. They've all got protective equipment in place so that it isolates that. So you can imagine there's ECGs everywhere in the hospital. So yeah, exactly. So just making sure that when the check comes up on the machine and wherever you go to work, whatever service you end up in or place that you end up in, it'll have a manual with it and it'll come up with the check. Paper speed generally doesn't change. You can override the amplitude of it, especially if you're wanting to look at, fine changes, even if, if you want to really hone in on ST segments or it is a very fine, a heart block or something you really want to hone in on. And as Georgie said, make sure that you document that on there. But again, the machine will come up. And if that's just something to check, it's usually preset to that. You have to go in and override that if you want to change it. But that's why we have that. It's more controlled in an uncontrolled environment such as pre-hospital care.
Sorry, Zoe, I'm not sure what you mean by recompression chambers. Is that a suggestion about something that could be an interference? Going on from that, if Zoe comes back to us, we'll go back to that. Confirming our electrode placement. What are our sorts of things that we're looking for in terms of our electrode placement? What sorts of things do we need to check?
All electrodes that you're referring to? Stickers in date, excellent.
Stickers in date, excellent.
That's right. I mean, you don't know. You might turn up and that packet of electrodes has been sat in the back of the truck or sat in the sedan at the back seat there in 40 degrees of Brisbane weather.
I can honestly say, Jay, I've never checked the stickers in date, but it's a really good practice, and I think shame on me. It's a great point.
In date or functional, sometimes you pull them apart, they just disintegrate. It's like, oh, this one's not too flash.
Yeah. What else are we checking about our electrode placement? Just on the fire risk with the increase, actually, I think I've realized frequency on ECG doesn't really affect. Okay, perfect, thanks. Body landmarks against lead name. Yes. So what sorts of things would we find if we had incorrect lead placement? It's our kind of giveaway on our 12 lead ECG.
Are there any red flags that we look at to think of, okay, with this doesn't look right, we've got the ECGs in the wrong spot?
Like if one of your leads is upside down, maybe?
Absolutely. Any suspicious ones? AVR, absolutely.
Yeah.
Oh, sorry. Yeah.
Correct. Yeah.
So if AVR is positive, that's a very quick sign for us, because remember AVR is sitting on that right side and we're expecting the voltage to be going away, not towards. So if AVR is negative and 1 is positive, then that's a good sign. What other sorts of signs should be in the same direction? Those sorts of leads. Why don't I unhide this one and we can talk about this one. One and B6, fantastic, Kate. Yeah, absolutely. So lead 1 and also B6 should always be in the same direction. And that's because they're both looking at exactly the same areas. So that's kind of a quick check. So we look at AVR as negative and lead 1 and B6 as positive. Any other sorts of signs? The leads are all, sorry, Gareth, I think there's actually a error in Milo. It should be the lead that there are no isoelectric limb leads. So that would mean that none of the limb leads are just flat lines. That would be suspicious that we either have incorrect lead placement or yeah.
Which lead would you expect to have the highest voltage or the highest amplitude if we were looking at a normal 12 lead or a diagnostic ECG? What's our main lead 2? So because that's the main lead, isn't it? So if lead 2 is the main monitoring lead, I'd expect the other inferior leads, AVF and limb lead 3, to look very similar because they're sitting next to each other. So sometimes you can also check by looking at the limb leads, and as you've already said, Kate, 1 and V6 lateral leads, so they're going to have a similar perspective there, or view, I should say.
So the next part of our ECG that we need to look at to check that it's also diagnostic is talking about our R wave progression. So that's talking about in V1 through to V6, we should see our R wave increase, and it should be at its maximum or its highest voltage in either lead 4 or 5, but ideally lead 5, and then it might just be smaller or the same in V6. So if we don't see that good R wave progression, that can be a warning sign for us. But the first thing that we need to do if we don't see good R wave progression is check the placement of each of our leads. All right, so what we're going to do is break up into groups and do our safe interpretation of the next couple of ECGs in our workbook. So if I break you up into groups of maybe 3, then we're going to get through our first couple of ECGs on our workbook. Are there any questions before we go? I might just post the principles over here. No, I can't. Any questions if I break you up? All right. Good luck, and we'll see you in 5 minutes or less than 5 minutes.
I'm not sure if you wanted to.
Okay, no group 1, and can we have group 2?
Have you got your sheets there with the safe principle on them, or that sheet that was before? And you just read off that, and then we can apply it to this.
So Emma's starting us off with the speed. Perfect. And the amplitude is confirmed in the calibration box.
Does everyone understand them? What you mean by the calibration box? That big box there, two big boxes, that's it. Zoom in on that. See that? We've also got the times 1.0 there as well. Is it also another confirmation? Yeah, that's it. So that's, yeah, okay. We just had a few questions of what is that big box, that all the big, yeah, those two big boxes there. That's what we're referring to.
So this is our S, this is our A, this is our F, and our electrode placement. How can we check our electrode placement now? AVI is upside down. Our E. What else about this ECG? Can we check that our electrodes are in the right spot? What are the two leads do we need to check are in the same direction?
V1 and V6.
Close. V6 is correct, and 1, yes, from Alison. Okay, so this is also our E. This is also our E. So we've got no isoelectric limb leads, and apologies for the inaccuracy on this on Milo. I'm going to correct this on Milo after this tutorial, but we're talking about none of these leads. Oh, sorry, hang on. I don't know why that's gone funny there. But none of these leads are isoelectric. So none of them are just flat. We can see the P, the QRS, and the T wave in all of them. Then if we head over to our R wave progression to talk about what Gareth was just referring to. So we're looking for our QRS complex to increase each time. So we see it go from maybe 3 small squares here, and it increases up to V4 to 10, 12, or 13. So we've got 3 to 13 small squares. So each time we go up from V1 to V2 to V3 to V4, we're increasing until it reaches a peak in V5 with maybe 15 small squares. That's 3 boxes, our R wave. And then V6 is no bigger than V5. So we're seeing that R complex continue to increase through our precordial leads. Is there any questions about that?
People understand why we look at that for those V leads?
This is probably a good opportunity. You need to go back a step and go back to the views of our heart and the precordial leads. Yes, absolutely, Chloe. We are looking for signs of ischemia. And to Zoe's point, because the leads are closer to the apex of the heart, absolutely. So I don't know if I've got the slides up here. No, I haven't got the slides up here. So when we're talking about our ECG leads, sorry, I'll just paste this in here. Hang on. Doesn't like me pasting something in.
Have you got a picture of them? in the notes or something.
Yeah, that's what I'm just trying to work out why it's not allowing me to pay something.
But view of the heart. I don't know if I can share. Can I show one? If I can find one.
Mhm.
I'm not sure if I've got one.
What about this one? Can we see this?
Yeah, positive. Yep.
So when we're looking at the precordial leads, last week we were talking about our augmented leads and the view that they're looking at of the person in a horizontal plane. This week we're talking about our precordial leads when we're looking at the views of our heart in a horizontal plane now this way. So as if we're cutting across the heart this way, whereas before we were looking at the heart as if we were looking at this plane. This week we're looking at this cross section. So as you can see in like this one, the leads that we're looking at as we go from V1 round to V6 should be increasing. But the point at which, if we, I don't know, can you still see it if I'm over here?
No, we're on the same page as we were before.
Perfect, yeah. So if
you go back to the...
If we're talking about where the majority of our conduction pathway is going, we're seeing that it's going this way, as we did with lead 2, the same sort of principle. The majority of our conduction is going towards lead V4 or potentially V5. So we should see the largest spike in our QRS complex in either V4 or V5. And then obviously V6 is looking at the ECG from the heart, sorry, from this side. This is where we're standing over here. Then it's going to be a little bit smaller than it was in V5 and V4. Whereas in V1, we're looking almost perpendicular or from the other side up in the right atrium. So we're potentially going to see that as a smaller wave or potentially negative. Any questions about this particular principle?
Does everyone understand that? That you're looking at two different planes of the heart? That's what these precordial leads, all these V leads give us. They give us the horizontal plane look, and we can look at places that we can't look at with just our limb leads. So for instance, V1 and V2 are septal. We couldn't access that before. V3 and 4 are anterior. But we can't, without these leads, we haven't got that view if we just rely on limb leads. So, and yeah, so it looks different. Everyone, that's a really important point to try and remember and think of. Is everyone 100% squared away with that?
Sorry,
It's okay if you're not.
Yeah,
Go on, Gareth.
I'm not.
Okay. Yep.
Georgie, can you go back to the diagram that you just had up?
Yeah.
On the right-hand side, as I'm looking at the black and white drawing, that doesn't look like a right cross section through the heart.
Yes.
Do you want another
As in,
picture?
You want another picture? Okay, let me see if I
Well,
can find
I
it.
give you, I've just put into the text the picture that's in the notes from this week.
Yeah.
So what's been confusing me is that the transverse sections and the cross sections seem to be getting jumbled up.
Yes. So effectively, when we're talking about the voltage of the cross sections, whether they're transverse or not, we're still talking about the voltage going towards the positive lead. So in our lead 2, we should see the highest voltage, but in V1 to 6, the voltage is still heading in that direction. So we still see quite a large spike, but we won't see as much spike as we do in lead 2 or 3, for example.
Yeah, that makes sense. But if we had to draw a diagram of why that's the case, would we use the one from the Milo that I put in the notes, or would we use the one that you just had up before?
I mean, the one from the Milo in the notes is effectively referring to the same sort of principle.
Do you want me to try and find a picture?
Yeah, maybe a
Done the
different.
same thing. Hang on, let me see if I can find a picture. I'll try and see if I can find something that has a picture that might help, because it is hard. It's a really important thing that we have to try and don't worry, everyone struggles with this, including us. All right, getting the way the heart's way it's sort of situated and
So the one from the Milo and the notes is still looking at the transverse cross section as we had with the same principle with the previous example that I showed. So both are still looking at the cross section as if in that picture. So they're still looking at the cross section like this one, right? So either way, when we're talking about the precordial leads, we're kind of cutting the heart in half and looking at it from that. Now, when we talk about where the positioning technically is, we're kind of looking at B1 and B2, then B3, 4, 5, and 6 around here, and we're trying to capture that voltage. Sorry, Chloe, you've got your... Sorry, Chloe.
I've got a picture if you want me to try and share this one. It's just a different way of showing what you've got there. Do you want me to try and
go for it.
do that one? How do I do that? Where's my share button? Down the bottom here. Hopefully this works. Sorry, apologies if it's not, people. Okay, can you see this picture here? Is this showing an orange thing?
Yeah.
Okay, all right. So if we're looking at this 12 lead, okay, we've got two planes that we're looking at. We've got a horizontal plane, this circle going around, and we've got a vertical plane moving up and down. So we know that the heart sits in here in the center, right? We've got our limb leads and our augmented leads that are in this orange plane. They're in the vertical plane. So you can imagine this bottom arrow here, this middle bottom arrow that's white, that's effectively limb lead 2. So we know where the heart is in the middle of the chest. So the conduction is going to travel towards limb lead 2, which is why we get the greatest deflection for limb lead 2. Either side of that, we've got lead 3 and AVF. So the conduction is moving down this orange circle towards the foot. All right, so that's why we call it inferior. If we look at this, is my cursor working on there, Georgie?
Yeah.
Okay, if we look at up, thank you. If we look at up the top here, this is where our augmented lead AVR is. So this, you can see if we're up the top of this orange circle, then the conduction, as we know, moves down towards limb lead 2. So we can understand why this is a negative lead now, because it's moving away from the view, this view here, of AVR, all right? So you can see in this orange sort of circle, this is where our limb leads are looking at. And when we use the word limb lead, we include the augmented lead. Then when we add in the precordial or our chest leads, our V leads, we're actually, you can see where these black arrows are now. We're actually looking at the heart from a different angle. And we still know conduction's still going to travel down towards the foot here, but each one of these black arrows is looking at the view is going to be slightly different. And when we use the word view, we're going to see a different sort of, maybe the P wave won't be as in the same shape as if it would be if I was looking at the foot, for instance, because this is a different view of the heart. And the reason why this is so important, if we look at this, and this is where Georgie's just put this picture, now if we can see that this is the horizontal plane for those V leads, these V leads now are looking at different aspects of the heart. The conduction's still going to go down to lead 2 as the main vector or the main summation of the electrical output, but these afford us a different view of the heart. And the reason for that is because we place these limb leads around in a different area, okay? Does that sort of help out a bit with the different planes? See, by visualizing it as a vertical and a horizontal plane, we can see that it's the angle of what we're seeing, I shouldn't use the word angle, the view of what we're seeing is slightly different. Remember that analogy we used last week? Georgie and I sat there having dinner and we're in a dining room and we've got windows all the way around. If someone sat over here in a high lateral lead, they're going to get a different view of the conduction as it travels down towards the foot than, say, Gareth is if he sat down here at the foot view. He's going to see it differently. It's going to be represented slightly differently on an ECG. So if we go to an ECG, we'll see that if we go to an ECG, we'll see that the amplitude will be different, the shape will be different, and that's the reason for that. But it allows us an extra view into the heart. And I'll stop. Does that help at all, just with looking at that? I'll stop share now.
Yeah,
I'm not sure if that
it
helped.
works for me. I'm happy.
Does everyone understand? Sometimes it's a picture, and you know when you look at an ECG book, you're like, no, don't understand, no, don't understand, no, don't understand. Oh, there's a picture I understand. It's like that for everything. You just got to find the right picture that makes it work for you. And what Georgie's just put up there is exactly the same thing, but it's just presented in a different way. So don't be put off by the ECGs and the books. Just find something that works for you because everyone's different. I think we were talking about his, ours before, Georgie and I, and we're both like, oh, yeah, we like this, but we don't like that. Do you know what I mean? So everyone's different. And the more views or the more ways you can look at it, something may click, is what I'm trying to say. Anyway.
Anita, I'm still just a little bit lost on the how, it makes sense to me that when you look this way, as the electrical signal goes down your heart, it goes and you can see the changes in that lead. But when you're looking at this aspect across, how does that cause like a similar deflection in the line? Does that make sense?
It causes a similar deflection. The deflection's still going to happen, but because I'm looking at it from a different angle, I will see it differently. So if I'm looking at a house from a different angle, the front door may not be as square on for me as someone who's down the road looking at it. Do you know what I mean? The
Yeah.
front door is still going to exist, but I'm just looking at it from a different angle. And so it's like a view. We're still going to see it, but we get a different picture of it. Like if we're standing there looking at a mountain, we're all around it. We're all going to see a different picture of it. And that different picture allows us to see that aspect of the mountain or that aspect of the heart where perhaps my neighbour may not have been able to see it. So for instance, if I've got a septal view, we can't access septal views with just limb leads because there is no V1, V2. So if we don't have those leads, we can't actually view what's happening in the directly view what's happening in the septal area. That's really all it is. We're still watching the same activity, the same electricity or the same voltage is going through the patient, but we're just looking at it from a different view. Now imagine cameras set up all the way around the heart and we're taking snapshots of that as that voltage travels through. It's still going to go down to our limb lead too, because that's why it's our main monitoring lead. But it's only looking at an inferior aspect of the heart, isn't it? It can't tell me what's happening laterally because it's not viewing it from that angle. This is why we take the trouble of putting on those electrodes around the chest, so it affords us that extra view because we need to see if there's any electrical change in there, if that makes sense. And I'll be quite, it just sometimes a picture helps, and Georgie's picture is absolutely spot on. That's what I mean. It just sometimes you have to look at the whole picture and then suddenly you click because you look at these pictures and you go, oh, I've got no idea what you're talking about. I don't know idea. And then all of a sudden it makes sense if you just think about the different views of the that's all we're looking at. It just gives us that extra bit of information to be able to analyze that ECG in a more complete way.
Thank you.
Go on,
Well,
Kate. Sorry, Kate, go on.
Just really quickly, can I just clarify? So when you're talking about that horizontal plane, like when you look at the picture, to me, it looks like it's a cross section, but I think it's not, it's not necessarily a cross section, is it? Because it's kind of just looking at that it's almost surface level of the V1, 2, 3, 4, 5, 6. Is that right? Because it's not really going all the way through because it can't look at the posterior side of the heart. Is that right? I think that's where I'm a bit confused. Like it's just looking at that little bit. I'm such a visual person. I kind of have to see it in my head that V1's just looking at that bit of the heart, then V2 that bit, but it's not actually looking all the way through, is it?
No. So if we can imagine as well, I wish I had another picture now. What are we going to call them? The precordial leads. So the precordial leads, remember, are positive electrodes as well. So whatever electrode we're measuring from is from the positive electrode. So if I go into this example, that's why I was trying to use this example here. But whenever we're recording or measuring the voltage, we're always measuring it from the positive point because we're measuring how much is coming towards us. And that's why we, yeah, that's just what we use across the board for consistency. But the precordial leads are positive are positive on that side. So they're only measuring how much is coming towards them. But because they're mostly looking at the left side or the left ventricle mostly, that's what overpowers the majority of what we can see. So we can't actually see the other parts of the heart because the left ventricle is so much thicker than the other parts of the heart, that we just can only really see that. And so, for example, atrial depolarization is actually hidden within the QRS complex. Does that sort of answer your question, Kate? I'm going to try and find some other pictures to help me explain that.
No, yeah, I understand what you mean. I guess that's just where I find those diagrams difficult, because it looks like it's a complete horizontal cross section of the heart, but there's nothing on the back to kind of, you know, draw, like, yeah. I guess
Yeah. And if we
it's just
measure
looking at
V7,
the-
8, and 9, so when we talk
Yeah.
about V7, 8, and 9, we measure that, and it appears mostly negative because it's away from those leads. But again, the left ventricle is overpowering what we see. So we're still really recording the left ventricle. We're still recording exactly the same thing. It's just that we're seeing it from the back, which is away from us rather than towards us.
So those V1 to V6 are really a very detailed view, mainly of the left ventricle. Is that right? To sort of
Really mainly, yeah. Would you agree,
Okay.
Nita? But maybe you can see a little bit of the atrial or the
Yeah.
high lateral elements, but mostly, yes.
Yes, that's what they are. Septal anterior. Very hard to get an isolated view of the anterior aspect of that left ventricle. That's what V3 and V4 offer you. Lower lateral with V5 and 6, and then the high lateral come in there with 1 and AVL. Yeah. So yeah, that's a good picture. That's so you can see there, looking at where it is. See right V1 there on that right hand side, you've got that right ventricle. So if we know V2, remember this is a horizontal plane. These leads are going to look different to lead 2. But notice on the left side where that's placed on that chest, and you can see V1 all the way around to V6 where we've placed it on the chest there. That's got that window, it's looking directly at that aspect. Now, it's not correct, it doesn't have the conduction travelling directly towards it. We know it travels down towards the foot, towards the limb lead 2, but it's still able to view the amplitude. It's still able to view that aspect as the electrical conduction passes through that part of the conduction pathway. And if we look at a V1 lead there, you'll notice that that is a positive P wave that you can see, but look at the actual amplitude of V1. If you draw it along that isoelectric line, so past the T wave back, you'll see it's mostly a negative lead, isn't it? It's mostly negative. Then we go to V2. It's a bit more positive. V3, a bit more positive. And as we move to V4, you can see that's equiphasic. So there's half of that QRS is positive and half is negative. And then we move into 5 and 6. These are the different views of the heart from the precordial lead, viewing it as it moves down to limb lead 2. All it allows us to do is to access or to look at. Now, if you go to the right-hand side now and look at it, you can see that V1 and V2 are looking at specifically septal and at that right ventricle. V3 and V4 are looking at the anterior aspect, left ventricle. 5 and 6 are left ventricle on the lateral lead. All they do is they give us a window into the current, into the voltage as it passes through from that viewpoint. If we didn't put these V leads on, it's still got current passing, we've still got amplitude, we can still see it in limb lead 2. We've still got our normal limb leads and augmented leads, but what these V leads give us are these extra views or these extra areas to see what the conduction is like. So for instance, if we've got an isolated infarct and it's only occurring, say it's septal and it's anterior, we would not necessarily be able to detect this on a 6 lead, so lead 1, 2, 3, AVF, AVR, AVL. We would need these V leads to be able to afford us this window to see what's happening with the conduction. And all we know that we're looking at electrically here is depolarization and repolarization as a summation moving down towards limb lead 2. And if there's an error in there, if there's a coronary artery occlusion, if there's some problem with depolarization and repolarization, we would detect it best with the lead that's looking directly at it, which is why if you've got a septal lead, for instance, and we're looking at V1, V2, we're going to be able to see that potentially from that view. We may not see that if we don't have V1 and V2, if we haven't got our precordial leads on there. That's all a 12 lead, and then if you go to a 15 lead, that all it allows us is that extra view. Does that answer the question or help at all? It's a hard concept, I know. It is hard. We've all struggled with this ourselves.
Carl, maybe I can go into your question and then see if that helps as well.
So you mentioned something that you're only seeing the left ventricle. So does anything allow you a view of the right ventricle or the atrial?
Not really, no.
So if there's anything,
Um,
if there's anything wrong with the other parts of the heart, we can't tell.
No, we do a V4R, so we do potentially remove V4 and put that over onto the right side of the heart, and we can see V4R from there, but realistically, what we see is if we see, how do I explain this more? If we see a positive deflection coming towards V4R, then that's telling us, how can I explain this more simply, Anita? We still see the left ventricle. Either way, the left ventricle kind of overpowers it, but because we know what's normal and abnormal for the left ventricle, that's when we can see that there might be something wrong with the other part of the heart, because we're saying that if it's not going the normal pattern, why is it not going the normal pattern? Is it going towards someone somewhere else?
Yes.
Okay, so from our view of the left ventricle, we assume or we use that knowledge to discern if there's a problem somewhere else.
Yeah,
There
and it's
are
the
ways.
combination of the
Yes.
leads, though. It's not just one lead that we look at. So, for example, if we saw everything is normally traveling towards the left ventricle, but then we look at V4R and it's positive, then we know then the combination of those two factors is what gives us the hint that something abnormal is going on. It's not just that everything is normally traveling towards lead 2 as it should be. It's that everything is traveling to lead 2 as it should be, but also we see depression or elevation somewhere else. And that's what gives us the hint that that might be that area of the heart that's impacted.
Okay. Kind of got that. Okay.
We'll go over this
We're going to
again.
go over that a little
Okay.
bit more in more detail, but yes, we basically look at the left ventricle. Sorry, James's group.
Hi, we were just wondering, in that diagram you showed us last, where all those pericardial leads pointed to the middle, like where is that middle point? And is that an anatomical feature? Is that just lead 2? Yeah, in the one
That
on the
one. So effectively, I mean, as it says in this diagram here, we put the leads in the different spots around here, right? And the central point, remember the ECG, what's it called again? Wilson's point?
Wilson Central Terminal.
Wilson Central Terminal.
Actually, I know.
That Wilson Central Terminal is the point at which it measures from, and it measures based on that central point in the terminal. So the ECG automatically calibrates using the limb leads. It calibrates that central point, and that's the central point that it measures everything from and towards. So yes, there is a central point, and that is a relevant point, and that's how it calibrates amplitude basically, and how much voltage it wants to measure on the paper. So yes, it does have a central point, but through that is what we can measure the different precordial leads, is how much we're expecting to find in all those leads and how much we actually find in all those leads.
So it measures from that point out, and that's what we see. Yeah, okay.
So that's kind of the negative point of the...
So we would be standing here. Oh, hang on a second. Wrong one.
I get
We
the
would be standing there, you know?
from, like, that central point is the one bit that was confusing me at least.
Yeah. So the central point towards us standing in all those different spots.
Yeah. This is probably a bit of a basic question, but is there like a circuit running through because of our electrodes, or is there just like, are they just measuring, or is, I don't know, how do they, is there a central point? Or is that just like, accept it, don't worry how it got there, it's there.
Can you ask the question again? So how does it know there's a central point? Is that right? Am I correct in that? So that's largely about the augmented leads, where not the augmented, like lead 1, 2, 3 and the augmented leads, is that it calculates the distance or the I don't know what is the word it calculates, but it calculates whatever the amount between that. And then that's how it measures across. So it calculates it for all those 3 views. So you couldn't do, for example, V1 to V6 without your limb leads on, because that's how it calibrates its like voltage and amplitude. Is that probably a good summarization of it, Anita? You would probably know this better than I will.
Yes, this is, so these are unipolar leads. V leads are unipolar. They've got one positive. Remember, our only bipolar leads are our limb leads with the positive and the negative, right? That's why we've got that central Wilson's terminal, and all it does is it adds all this together, all the voltage that comes in, it adds it all, and then it will compare it to a singular lead coming in V1. So therefore it'll average it out. This is the amplitude for V1. Does the same for V2 all the way around to V6, V9, whatever you want to use. So the idea here is there is a fictitious point there that it's referencing from, but the importance for the ECG is that the lead you are looking at, V3, V4, for instance, allows you to access that view of the conduction from that point of the heart. That's the important point, because that's the window we want to look at. The machine's calibrated, they do it all. As long as we make sure it's a diagnostic piece of paper, that we're looking at ECG, the paper speed, the amplitude, the voltage, that's the right patient, that we've got the leads on the correct way, then the machine will automatically calculate that for us. That's how they're designed to, that's what they're designed to do. Our job, therefore, is to look at that view of the heart. We've got a camera, we're taking that view of the heart, and we're watching that conduction travel down the normal vector to lead 2, but we're seeing it from a different angle. So if there is a delay in depolarization, repolarization, and we see ST segment changes, for instance, we know we've got a delay in repolarization in that ventricle. The thing that gets confusing here is that we can use this 12 lead, use these limb leads, because we can use them to look at other aspects of the heart by looking backwards up through the through the voltage changes that we see. And we'll talk about reciprocal and facing leads and contiguous leads and all those sorts of things a little bit later. But there are ways we can do that. For us right now, what we want to think about is we've got 12 lead, a 12 lead image. We've got 12 views or image or ECG strip here with a rhythm running through. That allows us to look at the depolarization and repolarization from that angle of the heart looking in. So septal, as you can see here, we've got V1 and V2. They're our septal leads. So they afford us a septal view of the heart. V3 and V4 are anterior. They show us the anterior portion of that left ventricle. And why the left ventricle gets dominance is because it's just bigger and having more muscle mass. It's bigger. It has more voltage to it. So it's going to outplay anything else. Doesn't mean we can't see other aspects. Of course we can. So that's what we want. That's what we're trying to look at here in terms of the view or the angle of the heart that is being viewed. And then what we want to do is we want to cross-reference that with the anatomy of the heart. So who is exactly perfusing that left ventricle and so on. I hope that helps answer the question.
So effectively, I mean, there's a million pictures, and we will definitely try and show you a million pictures so that hopefully something sticks, as I think Chloe said. But when we're looking at our ECG, it's really important to know this kind of format, because this is like a quick reference guide for what the area of our heart that we're looking at, right? And that will correlate to our ECG tracing. So they're kind of the quick reference guide, but this is a good picture, I thought, because it talks about the different areas and color codes with where you're actually looking at. So for example, the inferior parts we're looking at over here, the lateral parts we're looking at with the purple sections and so on. All right, we're gonna move on a little bit. Is that okay with everyone? As you know, this is going to be an intense subject, and we're going to keep coming over this in different ways. So please feel free to just throw the questions at us, and we will try and explain it in different ways if it is useful. But we're just going to go on and do one more safe tracing, and then we'll move on. So this ECG, oh, sorry guys, tried to lock it, but I haven't. All right, so with this ECG, are we, is this an ECG that we could use? Does anyone feel free like commenting or putting the mic on? So just quickly, is our speed okay?
Yes, speed's okay.
Speed's okay, fantastic. So we've got our 25 millimeters per second. What else? Ideally get a better trace. Fantastic, Chloe. Especially in that AVL 1 and 3. So it looks like maybe one of our limb leads is picking up a bit of artifact. So what sort of things could we do if this is a bit suspicious? What lead do we think is picking up that artifact? Yeah, left foot or even left arm, maybe. Because we've got lead 3 involvement and lead 1 involvement and AVL, and the common point is that left arm. Yeah. Okay, so maybe a better training. So our amplitude, is our amplitude okay?
Yes.
Perfect. And our frequency, is it okay too? Fantastic. So from Gareth. So frequency on this one is 0.15 to 150. So what does the approximately 50 refer to? Anita, another group actually asked me this question as well, and I'm not sure, but I'm assuming it's an average. Yeah. So it sounds like the average of the frequency that it measures, so how sensitive it is. But yes, to Emma's point, we should start at 0.05. So realistically, this is probably not a great tracing for us to use because of that. Other elements, if we were to ignore the frequency for now, what about our electrode placement?
Just going back to the frequency thing, have 0.5 as well as a starting point.
I've always been told 0.05.
Earlier you were saying you could have 0.05 to 40 and 0.5 to 150 or something like that, but maybe I was just missing the 0.05 every time.
Usually 0.05.
Okay. 0.05.
I
I don't think it's sensitive enough if you don't put it as 0.05.
Okay.
Again, the machine will tell you. It's usually whether it goes to 150 or 40 or 60 as the upper. Again, it's dependent upon the machine, the setting there.
But I will quadruple check that, but it should be 0.05. So yep, Milo might have a typo. It does say 0.5. All right, so we'll change. So Milo has 2 typos then, so it should be 0.05, and also the limb leads should all be not isoelectric. So if we go on to our electrode placement, so our limb leads are not isoelectric, are we happy with that? What else are we looking for in terms of our electrode placement?
I think we want to also have the 1 and VR in opposite directions, which it is.
1 and AVR in opposite directions, and 1 and V6 in the same direction.
Yeah, and then the QRS growing over that waveform, as in V1 down to V6, where V6
Yes.
mustn't be any bigger than V5 or something.
Yes, absolutely. So we see from V1 through to V5, we see it continually growing and it peaking at about that V4 or V5, and V6 is no bigger than V4 or V5. When you say limb leads, does that include augmented? Yes, Alison, it does. All right. Is everyone happy if we move on from safe principles? Because I'd like to talk about axis deviation if that's possible. Is there anyone who want me to stay on safe principles? Big now for hold space. All right. I'll post answers for the rest of the safe ones on the tutorial page. All right. So we're going to talk a little bit about axis deviation, and this goes largely off the back of what we've just been talking about when we're talking about the the vector of the electricity, or where the majority of the electricity should be heading towards. And so obviously we know the majority of our electricity is going to be heading towards lead 2. So we're expecting that our QRS complex is going to be mostly positive in lead 2. Is there any questions about that? I might move on straight away to left axis deviation then.
And Georgie, I've just found a LifePack 15 data sheet that I can put up in the chat, and it actually gives, I'll take a page here, it actually gives you the frequency response for, I'll see if I can just put it in the chat here so people can see that it actually gives you a frequency range for that. So the monitor, the paddles, and then 12 lead ECG diagnostic. So here it's got 0.05 to 50 hertz. And I can put the link in there. So that will be a data sheet for that, just so people have got that there, if that helps.
Definitely. Thanks, Anita. So when we're trying to work out the direction of the electricity going through the heart, sometimes it might deviate towards more the left or towards more the right. And there are lots of reasons that can happen in general. Maybe do you guys want to type in what sort of reasons that you think that might actually happen, why we might see left axis or right axis deviation? Pregnancy, great one, Zoe. I haven't got that in my notes, but that is a very good point.
Asthma, extreme asthma.
Extreme asthma,
Or
absolutely.
COPD.
Would that be during an acute exacerbation, or is that just all the time that someone with asthma or COPD would have an axis deviation?
Usually acute.
Okay. Like lung pressure, difficulty things?
Affirmative, yes. Yes, sometimes PEs, those sorts of things, asthma can change an axis.
Yes, to Katie, PE is a good one. Will we see that more in right axis or left axis, do you know? Absolutely, Chloe. We've got MI, left bundle branch block. PE is right, yep.
Right, that axis deviation is like a little tilt, or is it like?
So it's where the majority of the voltage is heading towards. So, for example, if it's shifted from heading normally down its normal path down the septum, if it's heading instead towards the left or towards the right.
Yeah. Is there also just natural variation between individuals? Like, will some people have like a kind of left tilted heart and some people kind of more vertical or whatever?
Yeah, absolutely. And although you might see minor left and right axis deviation, you won't see significant or extreme left or right axis deviation, because that can actually, that's normally a sign of something else, like one of these examples that we're talking about, rather than like a normal variant for someone.
Right. So is it kind of easy to notice, like when it's deviated?
Well, we have to assess it as if it's in there or not. And there's a couple of different methods, which I know are on your Milo, but the easy way to sort of talk about it is looking at leads 1, ADF, and lead 2. So because we know where each of the points of the leads are looking at, basically if we see something that is looking in a different direction than it should be, then that's effectively kind of our warning sign that there might be axis deviation, as sort of a general sort of summary. So the first lead that we probably are going to look at is lead 1, which should be pointing in a positive direction. Now, when we're talking positive direction, as it says up there, we're talking about the R wave being mostly above the isoelectric line more than the S wave below the electric line. isoelectric line, sorry. So we're looking at that to be mostly positive in leads 1 and ABF. Now, this is actually not a great picture because I think this picture talks about it easier when we talk about adding in lead 2. So if our lead 1 is looking at, for example, the left side, so it'll be over here. If lead 1 is we're over here and we're looking, then we're seeing mostly positive. So we should see mostly the direction heading towards lead 1 and also to lead 2 as well. So that puts us in this like happy zone over here that we're looking at, where the most of the direction is heading in the normal direction that we're expecting. But we do have this little zone here where we're still accounting for the fact that even if it's mostly positive in lead 1 and lead 2, it still could be abnormal. So we add in ABF and that helps us kind of narrow that zone of what we're looking at, which is if it's mostly positive in lead 1 and lead 2 and ABF, then we're on the average, we're in this quadrant over here where the direction of the voltage is heading mostly in that direction. Are there any questions about the sorts of leads and how we're looking at the same thing across the different views? Yes, there are. Go for it, James Tim.
I'm sure there's a lot that I don't understand at this point, but yeah, we'll revise.
Okay, I might go on to left axis deviation then, which will hopefully, I wonder if I can keep it in the same sort of quadrant here. So, for example, hang on a second, let me bring up my little people over here. So, is everyone able to see everything at the same time? Yep. All right, so in lead 1, remember we're standing up here, right? We're standing up there for lead 1, we're looking over there. So most of the direction is still heading towards the left, right? So in left axis deviation, we'll still see the majority of our QRS voltage heading towards both lead 1 and lead 2 in that instance. Sorry, so for left axis deviation, does this mean the height is kind of sideways with the apex pointing left upwards? I don't know if the apex points left or upwards. Anita would be able to correct me on that, but it does mean that the voltage of the electricity is heading more to the left than it is to the right.
Yes, because of the axis shift. That's correct. So if you've got left ventricle, for instance, if you've got in left ventricle enlargement or hypertrophy or, systemic hypertension or aortic stenosis or something like that, AMIs, those sort of things, anything that changes, we're talking about left, aren't we? Anything that changes the axis will, by definition, change the conduction, the trajectory of the conduction, which is why we see the change in the positive and the negativity between a lateral and an inferior lead.
That makes more sense. I was kind of imagining the whole heart kind of twisting upwards.
No, it is slight because of and for some people over time, for instance, you can imagine if you've got someone with massive hypertension for years, or they've got, the actual left ventricle becomes bigger because it's got, congestive cardiac failure, and they've got hypertrophy or something like that. So you've got that mass that changes. It's a slight axis change, and that's what causes the shift in the electrical conduction, and why we see it as a change in terms of why it's called an axis shift, because literally the axis has shifted, as I'm sure Georgie's going to sort of explain now. But does that answer
the question? I can't remember who asked that. Was it Zoe?
Yeah, kind of. I think I wasn't so much thinking about the electricity. I was thinking that the heart's like turned itself upside down. So that helped me a bit. Thanks.
Not quite upside down, but there is a slight shift in Yeah, there is a shift in it. Yes, absolutely. And that, you know, if you've got extreme situations, it could be increase in muscle mass, it could be changes in pressure. So we're looking at PEs or extreme asthma and things like that. That will have enough pressure to change, but not upside down, nothing that drastic, no.
So if you're thinking like pneumothoraces or like we're talking about the asthma or something like that, like we're thinking, oh, that could potentially shift the axis.
We would really like to second Kate's question in the chat, which is just basically there is an anatomical shift in where the heart is, like it changes location in the chest, but also does the electrical current change the way it's going through the heart? Does that make sense?
It doesn't change location. It still stays in the same spot, but it I guess it does change. It changes
Pivot?
Yeah, like does
pivot. Yeah.
the heart does it move like that?
Pivot is probably a better word. We're not moving the heart to a different part of the the chest. Yeah.
But the electrical stuff conduction changes, and that's what we see on the ECG. And
it moves, but yes, yes.
The physical movement of the alignment of the heart, or it could just be because like there's a section of the heart that's died, and so electricity is not going through that. The heart has moved physically, but the electricity movement has. So it could be both.
Yes. Yeah.
Nice.
So it could be both.
Yeah, effectively.
Also either or. Okay.
Yeah.
Right.
Thank you.
Thank you.
So if we have left axis deviation, for example, and we are looking at, for example, lead 1, 2, and 3, I mean, whatever method that you want to use, there's a couple of different methods, and there's a couple that Craig went through on Milo, but either way, you're looking at, is the positive and the negative different from what it should be? So the first lead that I always look at is lead 2, because it's the one that I'm expecting is always going to be the normal one. So if lead 2 is negative, then that's our big warning sign, because we know that that's either happened potentially, as James's group said, because there's been sort of prior infarct or some reason like that. So we're seeing that mostly the direction of the voltage happen away from lead 2 in the first instance, which can be a sign of that. Now we combine that with our understanding of what's happening in lead 3, 1, and AVF, and we can see. Anita, why haven't I got a picture here of the axis deviation circle? Hang on a second.
What do you need? Do you want me to look for something?
Deviation I'll see if I can.
You want the circle? I've got
Yeah,
something.
you know what I mean, like the picture with all the
with the pie with the different.
Yeah, I've got it.
You got
I was
it?
like, I should have put that in here. Where are we looking?
Do you want me to share my screen? I've got a picture. I can help.
Put it in there, hopefully.
Oh, you got it? Okay.
Yeah, thanks. We all know the one that I'm talking about. So then when we're talking about left axis deviation, if we see that there's a large amount of voltage direction towards AVL, for example, if we're over here and we see that the positive is now happening towards this direction, that's a warning sign for us, because if the QRS is happening mostly towards AVL, what we should see is it to be pretty isoelectric, if not not isoelectric, sorry, perpendicular view. So we should be looking at the heart from the side, not from all the voltage coming towards us if we're standing in AVL. So that's a warning sign for us if we're seeing that the most of the positive direction happens up towards this direction. Now, we can have different variations of it, and that's why we typically look at 1, 2, and AVF, because that's what our normal direction of positive should be. So we should normally see positive in all of these leads. But if we start to see negative, for example, in AVF and lead 2, then we know that we're heading towards this direction and we're starting to become more positive in an AVL, then we know that that axis deviation is probably happening towards that. Now, the opposite is true of right axis deviation. So if we start to see lead 3 become positive and even sort of a perpendicular AVR, so if AVR started to look like AVL, then we would know that we're starting to head towards extreme axis deviation over here, or even right axis deviation. Summary, does that make sense? Pause point.
Sorry. So just to kind of like recap that.
Mhm.
So if the AVF begins looking like an AVL,
Yep.
that could
Yes, go on.
indicate left deviation, but if it starts looking like an AVR, it could be right deviation. So if it starts looking like a different either of those different ones, that's what indicates it. Is that like in summary, or did I just get that wrong?
Not so so the most positive lead is going to be lead 2, right? So we're going to kind of agree on that if in the perfect sort of world, but obviously there's a variation on everyone. So if AVF, let's talk about a more extreme example, but if AVF is sort of on the halfway point, so imagine it's like QRS is like perfectly even, then that's when we're starting to think that AVF might be a perpendicular sort of view, or the voltage now we know is not heading mostly towards AVF, it's heading across rather than towards AVF. So that's when we might start to see that right axis deviation. And we'll also see that mirrored in lead 3, where we'll also see a really positive deflection in lead 3. So it'll be mostly positive in lead 3. So for example, I think I've got an example up here. Lead 3 will look like mostly positive, which is where we're sort of looking at there. What the combining sign is when we look at the opposite side. So for example, if we see mostly positive in AVF in 3 and 2, but we start to see a negative in lead 1, we now know that the voltage is heading away from this lead if it's heading towards this way. So we'll start to see a negative deflection in lead 1, which is what is suspicious of right axis deviation. But if we see, for example, it's becoming more positive in lead 1, it's becoming more negative in lead 3, then we know that the direction is now heading in this direction. And the electricity is heading up towards 1 and AVL.
Sorry. So basically, is it like the more positive it becomes, it's more likely to be left, and more negative, it's more likely to be right deviation?
It depends on the lead that you're looking at, but yes.
Yeah.
Do you want to have a look at an axis deviation to have a look at
Yeah,
one?
let's look at one.
Do you want me to share this? How do I do that again?
I think this one should be.
Have you got one there? An axis,
Next
a left
one should be.
axis, and then you can sort of show like an actual ECG. One of those might be.
Look, I think this one. Okay, so what's our suspicious sign out of this one?
So think about the wheel that you just saw, right? And look at the positivity or negativity. Start with those limb leads.
Start with our favorite lead. What's our favorite lead that we need to look at?
2 should be very positive, but it seems to be both positive and negative.
All right, so if we know it's positive and negative, we now know it's going to be heading in a different direction, right? Because we're kind of looking at it now perpendicular, right? So that's suspicion number 1. So what lead should we look at next? Or could we look at next?
3 should also be positive, but it's gone negative.
Yes, for sure. And AVF, should it be positive or negative?
Positive.
Positive. Okay, so 3 and AVF are now negative, and 2 is pretty isoelectric. So if we look at our, let me go back to our picture now. So we know what we're looking at now. Oh, here we go. I had one here. We should, no, that's not a good one. So we said that 3 and AVF should be positive and 2 should be positive, but all of them are negative, which means the direction of our ECG is heading this way. So what do we think it is?
Who should be positive then? If it's heading away, if we've got this left axis shift,
do we expect
2, 3 and AVF are all negative, where they should be positive, and the current voltage will, because of the axis shift, should lead AVL and 1 be positive or negative here? I'm going to go back to that chart and have a look.
Positive?
Yeah. because it's heading towards it. If the left axis shift, it's going to be heading towards it. So if we look at our ECG, that's one we had before. Yeah, look at lead 1, positive deflection. Look at AVL, positive deflection, as it should be normally. But that's abnormal because we've got 2, 3 and AVF, all our inferior leads, where it should normally be positive. They're all negative. So now we've got the issue where we've got it moving towards away from the normal axis, which is their normal purple area down there. You see the normal axis QRS moving away from there. And it's actually because we've got an axis shift, we've got a change in the direction of the actual current voltage. And you can see 1 and AVL are positive, 2, 3 and AVF, which are all your negative leads. You can see them down there in the purple is our lead 2, our favourite lead, and AVF is its neighbour. So here we've got an abnormal ECG, haven't we? We've got an abnormal ECG in the sense that it's not either there's something wrong with this. So when you put this on in a patient, left axis deviation is usually always abnormal, and reasons for that is usually due to long-standing left ventricular enlargement. So systemic hypertension, aortic stenosis is anything that's affecting that left ventricle, bundle branch blocks, for instance, inferior MIs. Yes, we can check more than that. Usually it's the corresponding opposite lead. So an inferior and a lateral lead will do it. Depends on what reference scheme you use. People do different ways, but usually it's those opposites. If you've got a positive in lead 1 and a lateral lead, so I'd also look at AVL because that's also a lateral lead. That is also positive. And I've got a negative in all my inferior leads. I start with 2, and I do clearly have negative in 2. I've got negative in 3, and I've got negative in AVF. There's an issue there with that because all of them are meant to be positive leads, and they're not. And if you look at that picture that Georgie's got at the bottom there, normal trajectory should run down to that purple area where normal is. So we should normally see a positive lead 2, 3 and AVF. Not happening. So the axis is actually shift left. And people with long-standing hypertension, stenosis, hypertrophy of that left ventricle, this is often a presentation that can occur with these patients.
Absolutely, Kate. And that's exactly why we went through our safe principles before this, is because to that point, if you have your electrodes in the wrong spot, then you will see that.
Everyone's got an axis deviation. Come on down.
Which is why we first check the electrodes, because it's kind of, we don't want to be like, oh, you have left axis deviation, when actually you're perfectly fine, and you just put the electrodes in the wrong spot. Literally nothing more embarrassing. All right, let's go into this one, and then we'll start. What about this one? And to Gareth's point, no, we don't need to check any. Well, yeah, you can get away with checking with 1 AVF and 2, but adding in 3 is helpful, and especially AVR as well. Basically, all of your limb leads is really useful, because then the combination of all the factor of them gives you the bigger picture. But you could get away with 1 AVF and 2. All right, so to Zoe's point, lead 3 is super positive. So we know now, looking at our picture, that we're mostly heading in that direction. All right, where were we? Sorry, are we on this one? Yeah. What else do we know? AVR is positive when it should be negative. Absolutely. But is it completely positive, or is it half-half? For sure, yeah. And our P wave is also negative. So apart from lead 3, what else have we noticed? What do we notice about 1 and AVL?
Very kind of half-half as well.
Half. Yep. 1 is more negative than positive. Yep.
As is AVL.
So if I go back to our little picture, so if 1 and AVL are sort of on the halfway line, or if AVL is mostly negative, then we know that we're not heading towards AVL, we're heading this direction. And we're sort of on the halfway point of 1, so it might be looking sort of perpendicular. So effectively, when we now know that our direction is also reconfirming we're heading in this direction. So yeah, we're looking more at right axis deviation. Is that making sense for everyone, or yes? Yes, no? Happy? All right. Do we want to sort of finish up there on the axis deviation side of things? We've got through not quite as much content as we had hoped we would get through today, but we do need time for it all to sink in. Yeah, okay, sure. I'll try and put the answers up for the SAFE principles on Milo, and I'm just going to correct the SAFE principles, and I'm sorry about the inaccuracy on Milo for that, but I'll confirm that on your Milo and put a notification update that comes out to you all. In terms of what I would love for you guys to do this week is in the remainder of your ECG workbook from today's tutorial, there's ECG examples for ST segment elevation and T wave evaluation. Against your textbook, it would be great if you guys could evaluate whether or not they're normal or abnormal ST segments and T waves, and start to identify that. And at the end of the week, I'll post the answers for those answers. And then I think at the end there's 2 or 3 12-lead ECGs, and it would be great if we could start to go through the steps that are on Milo. So your rate, your regularity, etc., going on from your 5 steps to your 10 steps to start to apply some of the things that we've talked about today, and also your ST segments and your T waves evaluations as well. Does that sort of summarize the homework for this week? Yep. Anita and I might even try and do a little mini recording and go through some examples of it so that we're explaining it later in the week if we get time. Yeah, go for it, Tal.
Quick question. How do we access this whiteboard?
Oh, you should have access to it all semester. Just be cognizant that we all do have access to it. And so just across the board, make sure that that you remember that everyone has access.
So how do we get to it? Sorry.
I'm just going to see if I can get a...
Is there a link?
Copy link. There we go.
Perfect.
I'll copy the link into your tutorial page. How about that? And I'll post it underneath the tutorial workbook.
Perfect.
And that way, if anyone who's listening to the recording can also make sure that they can access it as well. Any other questions from today? Yes, go for it. James is great.
Could you know how you said the homework, would you be able to write that into a little announcement for us? Because I didn't write down what you said and I've already forgotten.
Okay, no worries.
Sorry.
I'll write it down. I'll write it down.
Yeah.
Effectively, just keep working through analyzing the waves and the ECGs that continue on throughout the rest of the workbook in activities. I think it's 3, 4, and 5.
Cool. Thank you.
Lecture doctor is in the great videos. It's Craig. So Craig's he's an ex-lecturer that was here. So he is the one in the videos. Okay. All right, we'll leave it there, guys, and I'll try and put a summary announcement today of what happened in the tutorial, and we will go on with bradycardias and next week, and also more about 12-lead ECG interpretation next week. All right, thanks everyone.
Thank you.
Thanks all. Thanks for all your hard work.